Thank you, Irina, for inviting me. Today's talk is on responsible AI, which is a topic which has already come up in a couple of contexts this morning, with a promise not to explicitly mention large language models, just for something completely different. So I don't think we really need this slide nowadays, but just as a precursor to give us a sense of what fairness means, I've got a couple of recent instances of exposés, if you like, of where AI has gone wrong with real-world implications. So what we have on the left is an instance of, we were talking about CVs before, so Amazon doing naive things in terms of trying to do screening, and people showing that it has inevitably biases against particular demographic groups. What we have in the middle is Twitter. In this instance, it's in the context of computer vision. So the auto-cropping algorithm that's used for the Twitter users when you scroll through your Twitter feed, demonstration that the auto-cropping is biased towards lighter-skinned, younger, more beautiful, for some definition of beauty, individuals within the image. So, if you don't meet those criteria, you're likely not to appear in someone's Twitter feed. Is that fair? I think we could all agree that that is not fair. And on the right-hand side, you have instances in an NLP context where people have sort of shown across a range of different tasks where fairness has had implications. As a personal journey, I guess, into this space, kind of the road to Damascus moment for me, if you like, was in the context of what you would think is a perfectly benign application, the simple application of language identification. So I've got a document, what language is it written in? And it's the simple task of, we'll assume it's monolingual, so what single language is it written in? And to make it even more seemingly benign, we're just going to look at an English document filtering task. So it happens to be a Twitter feed, return all of the documents that are written in English. And you sort of think that, well, where is fairness going to rear its ugly head here? So this is work that David Jurgens and Yulia Tsvetkov at Stanford at the time did, where they showed across the x-axis you've got, based on the country of origin of a particular variety of English, a classification onto the Human Development Index of that country. So on the left-hand side there, you would have a country like Nigeria, so predominantly, largely English-speaking with a reasonably well-defined variety of English spoken in that country, but with a lower Human Development Index. And all the way on the right-hand side, you'd have a country like the US or Canada or Australia, say, with a higher Human Development Index. And what you have on the y-axis is simply the recall. And you have this horrible, horrible effect of the lower the Human Development Index, the worse the model does. So Nigerian English, terrible. Australian English, pretty good. US English, probably best. And so I'm, the blue curve here, in terms of the personal anecdote, is a system that we developed many years ago, something called langid.py. And this has this awful characteristic of it just does worse and worse for varieties of English from countries with lower human development indices. And even models which are trained to be more equitable, the orange line, you never get a flat curve. You always get some degree of disparity there. So what's this talk all about? It's trying to identify, quantify, and then ideally ameliorate these sorts of biases in the sorts of models that we're training. So then, in the context of NLP, what is fairness? And I'll rush through this slightly, given time constraints. So people predominantly talk about two forms of fairness or bias in terms of, we'll use the term modern large language models. So it's either fairness in terms of the representations that my model is generating. So if I take those representations, what I'm using to actually generate the outputs of my model, whatever that may be, can I unearth protected attributes, so whatever properties of the author or the target referent of the language that is encoded in that representation, where you would think for a fair model, it shouldn't capture these sorts of characteristics. So we don't want it to be able to capture any of these protected attributes. Versus empirical fairness, which is the more obvious case, in the outputs, can we observe these sorts of disparities? It does better for certain demographic groups and less well for other demographic groups. So I'll talk primarily about empirical fairness there. There's a fascinating interaction between the two, which I'm happy to answer questions about. So then the question arises, and it sort of seems like a funny one to answer, because intuitively I think we all sort of understand, roughly speaking, what fairness is. But the deeper you dig, the more you realise that there's a lot of subtlety here, and this is a lot of what the first part of today's talk is all about. So what is fairness, and what is it fairness in terms of? And then fairness how? So if we're trying to quantify fairness, how do we do that? And what assumptions that we bake into the method of quantification have then implications for the models that we're training, and how fair or unfair they may be. Also, very importantly, in NLP, there are very few tasks where we look at trade-offs. Trade-offs between, in this case, the raw performance, the accuracy of a model, say, and fairness, with the expectation that if I just go for performance, then I'm going to sacrifice fairness to some degree. If I try to go for as fair as possible a model, I'm going to take some hit to performance. So how do I balance those two up? How do I do that multi-target objective in optimization terms to sort of try to reach an optimal point between those two? And then we don't sort of talk enough about model selection, I would argue, in NLP. So given that, particularly in modern day NLP, we tend not to have a single system. Depending on our training seeds, depending on hyperparameter optimization, we get a family of different models that we're training, and we're trying to do some selection amongst them, which defines then a distribution across this frontier of performance versus fairness. So under that, how do we actually compare two models? Okay, so we're going to go through those in turn. Just by way of background, I mentioned this briefly. So we sort of tend to talk about source bias, as in who wrote this thing. So that would generally not be represented explicitly in the text, but there are all sorts of subtle, maybe sociolinguistic signals, maybe more overt signals than that in terms of the content, which allow us to, to varying levels of certainty, make predictions about certain attributes at least, maybe not quite the identity, but certain attributes of the author. So for this particular example, it's an adventure which reaches back to etc. If you read that, you probably get a sense of, show of hands maybe. Who thinks that's more likely to be a male? Who thinks it's more likely to be a female? Who doesn't know? Okay, and don't know is something that we're going to get a lot of. So there are a few more males there. Who thinks it's a young person? Someone in their teens, say. Probably not. Who thinks it's sort of someone in their 40s or 50s, sort of an older age person? Yeah, more hands. Who doesn't know? Again, doesn't know is fine. And this is a Guardian movie reviewer, a white male at the time, I guess, in his late 40s, and just the style of writing, the particular references to Golden Age Hollywood maybe is a bit of a giveaway, at least in terms of sort of priors. Particular expressions like devil may care aren't the sort of thing that you would expect a teenager to use. And then on the other side, you've got target bias. So this is the entities in the world that I'm referring to. So something like coreference resolution, if I'm referring to male reference versus female reference, getting disparities in terms of the same coreference resolver does better over male antecedents than it does over female antecedents, say. So today I'm predominantly talking about source bias. So then how does the literature work? If we're trying to develop fair models, de-bias methods, what do we do? So there are three predominant paradigms that people talk about. The first is pre-processing. So I do something to my training data, and the standard sort of strategy is, well, disparities come about because I have unequal representation in my training data. So if I can balance up the training data in some way, either explicitly through downsampling or upsampling in some way, or through instance weighting maybe. So I craft my data set in a certain way, and then I go away and train it. So this is what we call pre-processing versus in-training, where I'm trying to do the de-biasing on the fly. So I have somehow built into the objective for the model that I'm training some way of trying to explicitly do the de-biasing. So an example of that would be adversarial learning, for example, where we've got a base model across the top there, and then an adversarial discriminator down the bottom, which we're trying to use to what we call unlearn the protected attribute. So its job is to predict, if we had the CV case, for example, whatever it is, whether it's something about age or something about the background of the individual or something about the gender of the individual. Its job is to do that, but our objective is structured such that it does as bad a job of that as possible. And by doing joint training of the discriminator with our base model, backpropping through the same representation layer, we have this interaction to force the base model to not capture the particular artifacts of our predicted attributes of interest. And there are many other methods. This is just one example. And then post-processing is where we train a model, and then post hoc we do some manipulation to either the outputs or the representations that it's learning. So something like we do linear projections over the learned representations from that model to sort of have a post-processor to try to do some projection into a space which is hopefully less biased in something like iterative null space projection, for example. Okay, so these three different approaches. But what I really want to talk about is fairness. What is it? So if you look in the machine learning literature, you'll find a plethora of definitions of what is fairness. And broadly speaking, they're categorized across three families. So the first is independence. So the idea that I should have strict statistical independence between the predictions, my y-hats of my model, and my protected attributes. And if you think about this for a while, you realize that's a very strict criterion to try to meet, so much so that if I have any imbalance in my data, I cannot actually produce a fair but perfect model. It's just theoretically impossible to do this. So people tend not to focus on independence. They tend to use one of the latter two classes as the definition. So then separation is the idea that my model predictions should be independent of the actual label given my protected attribute. And just to be clear, the protected attributes are things like the binary gender, say, or race, for want of a better term, or age, or these sorts of things. And this is probably the most mainstream definition that people use, but you've got 8 instances there of slightly different instantiations of what separation is, mathematically distinct definitions of what is separation, with equalize odds being the favourite amongst those within NLP. And then sufficiency, which is the idea that I want my model to be equally well calibrated. So I want the probabilities that my model is generating to be equally good quality, as in equally well representative of whether that's actually a correct label or not across all of my protected attributes. Okay? So as I say, separation is the one that people use most in NLP. So okay, we've got lots of different definitions of fairness. That's going to affect how we define our evaluation metrics, but also potentially how we define our objective functions. But in terms of the simple, or what you would hope to be a simple evaluation question. So I've trained a model, I get outputs of my model, I want to sort of calculate numbers to be able to compare different methods. if we have a simple case of binary outputs with a binary protected attribute, so let's say we have binary gender, say, it's well defined. So I look at something like, if we're talking about equal opportunity, the absolute difference in the true positive rates across the different protected attributes. So I partition my test instances and I look at the true positive rate for each of them, and I want the absolute difference between them to be as close to 0 as possible. If it's 0, it's a truly fair model, which is very rare. Okay, but what happens if I go to multi-class tasks and multiple protected attributes, or higher arity protected attributes? So if I were to task you with, for two actual models, Model 1 and Model 2 here, so this is a profession classification task. I've got a biography, a self-authored biography for someone who's sort of advertising themselves on LinkedIn, say, are they a dietitian or a DJ or whatever? And I've got then a breakdown across these different professions, across the two intersecting protected attributes of binary gender versus the wealth index of the country of origin. Okay, so you have two columns each for male and female based on this wealth index. So if I were to task you with telling me for Model 1 and Model 2, which is the fairer, you could look across dimensions like professor, for example. That's pretty fair. They're all the same colour. We don't get any disparities either within this wealth index or across different genders for either of our two models. So that's fairly clear cut. Versus dietitian, Model 2 seems to be fairer, as in terms of the colour map. Those two are closer. Nurse, again, they're pretty similar. Whereas for DJ, Model 1 seems to be fairer. And I'm trying to do this across this cross product of these different protected attributes across the full set of these different professions. This is just a subset of them. It's a very hard task. It's not clear what the answer is. So how have people done this aggregation to give us a single figure of merit as to which is the better model? The answer is everyone's done their own thing. So as with any aggregation task, you can min, you can max, you can take absolute differences, you can take arithmetic means, you can take geometric means. You pick it, people have done it. And this is from the actual literature how people have done this aggregation. And of course, this has real-world implications if we're trying to say, out of two different models, which is better over a data set where it's more than a simple binary classification, binary protected attribute setup. So the first thing that we did here is to sort of say, okay, can we introduce some method to the madness? And I'm not going to go through the details, but we observed that, well, we can come up with a general form for how we're doing the aggregation in most cases by introducing p-norms in terms of how we're doing the group-wise aggregation, as in across our predicted attributes, versus how we're doing our class-wise aggregation. So depending on how we parameterize those two p-norms, we can get our max or our mean or our arithmetic mean or whatever across those two different dimensions. So, okay, fine. So then the question arises, if we come back to our original example, okay, so how big a deal is this? Does it really matter? So if we parameterize the two p-norms differently, do we actually see a disparity in the results for these two actual trained models? And the answer is very much so. So what we've done here is a parameter sweep across these two hyperparameters. Blue means that Model 2 is better, red means Model 1 is better, and pick your value and you'll get a different result. So where does this leave us? And so then, and I'm going to skip some of the details here, what we did in the first instance was to say, okay, given that you've got all these design choices in terms of how you parameterize your evaluation metric, what you really need to do is, from first principles, think about, well, what do I care about? Do I care about absolute gaps? Do I care about the ratio between them? Do I care about the raw scores? And then how do I do the aggregation? And came up with a decision diagram based on the values that I want to encode in my evaluation of fairness to get us to an outcome as to, okay, how do I parameterize the choice of the unit and the selection of these p-norm values. And I'm going to skip over the details somewhat, but happy to talk about it in more detail. So that part of it, I mentioned model selection and comparison at the start. So then we have this issue of, okay, so we've got different methods. So for INLP, for example, where we're doing these linear projections of the representations that are generated by our model, we can do 1 iteration, we can do up to 100 iterations, and we're sort of progressively projecting over those iterations. And what we observe is performance goes down, fairness goes up, and we've reversed the sign of fairness here. So higher fairness means a better model, a fairer model. So given this, where do I choose to select my cutoff? What is the ideal number of iterations for INLP that gives me the optimal result here? So obviously, I need to make some determination of, well, what is the trade-off between my performance and fairness in order to make that call? But ideally, if I think about it, is actually defining a distribution across the fairness performance range. And I want to be able to say not just, well, based on some preordained magic parameterization of the relative balance between the two, across different choices of how I do that parameterization, which is the better model. So across the full distribution. And again, what we find in the literature, the way that people have done model selection has varied a lot. And we've got 4 different methods here where we're using different model selection criteria that people have proposed. And what you observe is smaller is better, bolder is the best method based on a particular selection criterion. So for any given method, if we choose a particular selection criterion, at least once that ends up being the best method. So if every player wins a prize, but we still are no closer to which is the best method out of these. So what we propose instead is, rather than sort of looking at this as a point-wise optimization problem, what we should instead look at it as a selection process over the full distribution of values. So look at the area under the curve of the performance fairness curve that's defined by the distribution of the different models that we're generating for a given method, and do the comparison based on that area under the curve. To avoid this sort of situation that we have up here, for example, where model B is better than other models at certain points, but then model A is better. It's a bit like a horse race. At what point do you declare the winner? Where do you define the finishing line? Well, if we can do that as the area under the curve, we don't have to make these arbitrary decisions. We can look at that full distribution. Okay, so the first part of it, the conclusions are understanding competing criteria is a bit of a minefield, and we've sort of tried to introduce some structure to that minefield and tried to do it on the basis of design criteria. What do you really care about in terms of fairness? Design your combined aggregated metric on the basis of that. And then NLP sucks at model selection, and hopefully through this idea of the area under the curve of the performance fairness trade-off curve, you can do a fairer job of choosing between different methods, as in sort of how well they do holistically. Okay, so next part is to say, okay, all well and good, but all of the results that you've presented so far have assumed that you've got full access to predicted attributes. So basically, in order to train a fair model, you've required every individual represented in that data to completely out themselves in terms of the full range of values of whatever predicted attributes it is that you're interested in. And in many contexts, you just don't have access to that. People either, that there are sensitivities in terms of people declaring their protected attributes, or I just don't know what the protected attributes of interest where I'm going to get unfairness are. So yes, I can optimize for things that I know about, but is that to say that if I looked at other protected attributes that I perhaps hadn't thought of at the time, I would equally get fairness? I just don't know. So can we move beyond this requirement on fully labelled data in terms of our predicted attributes, but still attain fairness in our models? And it sort of sounds like an unattainable goal, right? Because I need labelled data. We're also addicted to supervised training. That what can I do without labels? And so in earlier work, we looked at the question of semi-supervised debiasing. So if we have partially labelled data, going all the way down to as little as 1% of the training data we have protected attributes, can we still get meaningful gains in terms of the fairness of our models, and sort of shown that, well, yes, you can. And relatively small amounts of data go a very long way. And further, that if you project predicted attributes from other domains or other data sets, so if I have a completely unlabeled data set with respect to predicted attributes, but have a secondary data set where I do have those, depending on the structure of the model. So if it's something like adversarial training, where I'm doing this joint training with respect to my target labels, but also with respect to my protected attributes, but the actual updates are decoupled, there's nothing to say that those labels for my target variable and protected attribute respectively have to be drawn from the same data set. So I can actually do this mix and match. It sort of doesn't work super well, but it works better than nothing. But what we were exploring in this work was, what if we have nothing? There's just no labeled data. And there are many contexts where this would occur, for legal reasons or otherwise, where we just don't know. And as I say, it partly gives us the hope of potentially future-proofing our methods over protected attributes that we possibly hadn't thought about. So the intuition, and I'll skip over the technical details somewhat, but the intuition behind this, which we can observe in these two plots, T-SNE plots, where what I've done is labelled the instances based on the protected attributes in colour. So you can see that the blue is our majority protected attribute. This sort of washed out orangey colour is our minority, where we're going to get the disparity. So we expect that our minority we're going to get lower performance for. So if we look at the loss per instance, and that's what I've plotted here in colour around each of my training instances. So the darker the colour, the larger the loss. Okay? So what we can observe is there's a fairly strong correlation between the label of the instance with respect to my protected attributes and the colour, the darkness of the colour. So my minority instances, they don't get enough of a say in terms of my model updates, and this is exactly where the unfairness creeps in, because they're underrepresented in terms of how I'm doing my model updates. But if I can simply use that observation of the per instance loss, does that give me a means of actually doing the partitioning of my instances? To say, if I simply identify what are my higher loss instances in green versus my lower loss instances in red, can I, to some degree, recover the original labelling of the protected attributes? And the answer is surprisingly well in this particular instance. And as I say, all we're doing is looking at the loss across training and doing this binary partitioning of the instances based on that average loss that we're observing. And on the basis of that, we're saying, okay, we're going to do proxy labelling of the instances, and we're going to do the debiasing relative to those proxy labels. So it's completely automatically inferred from the data. I'm not assuming any access at all to protected attributes. The only time that I did that was when I was sort of validating that this assumption makes sense over this particular data set. Okay, so that's the basic idea. Sort of the other part to it is to say, and I'll sort of skip over the technical details here, we can additionally look at some sort of semantic smoothing. So obviously, there's no guarantee that a given minority instances are going to sort of purely cluster together in a particular subspace with respect to my learned representations. I can get all sorts of anomalies in terms of singleton instances appearing in a region where they're surrounded by lots of majority class instances, and maybe that's the truth, or maybe that's more of an anomaly in terms of my calculation of the loss. So I'm going to do some semantic smoothing using simple k-nearest neighbours, again, not based on the actual labels, just based on my calculation of my loss with respect to my target variable to try to sort of smooth out some of these anomalies and just try to reduce the number of outliers. So that's the basis of the method. How does it work? I'm not going to drag you through all of the gory details in terms of the numbers here, but the answer is certainly a lot better than our baseline, and we're using our area under the curve again here. So our baseline in terms of doing nothing we have here. There are pre-existing methods either using a subset of labelled instances that we have in the orange, or another unsupervised method, versus using this proxy labelling approach based on the observation of the per instance loss. And we're doing this across 3 different debiasing methods. I won't go through the details of exactly what they are, but because once we've generated the proxy labels, we can combine these with whatever debiasing method you want. And if we compare that to the supervised models for this particular data set, we're certainly observing for the corresponding models a drop. But over other data sets, so this is our biography data set again, over other data sets we're observing very competitive results, largely the same as doing the full supervision. So we're very surprised at how well this method did. So the conclusion of this part is you can do a surprising amount with fully unsupervised bias mitigation methods using this simple heuristic of observing the training loss with respect to the target variable and get results that are surprisingly competitive. Just to finish up, I wanted to mention that we have a library called Fairlib, which has implementations of a large range of different debiasing methods and evaluation metrics, ways of visualizing the data. It's as simple as downloading it and importing Fairlib. You've also got data loaders for a lot of the standard data sets from both NLP as well as CV and ML. And I'm not going to drag you through the details, but simply using this and going back and doing a more thorough investigation of pre-published methods with respect to standard data sets under a budget in terms of hyperparameter optimization, we found that some of the sort of venerable methods which people had kind of used as somewhat punching bags in terms of their accuracy, like this iterative null-spaced projection method, actually do a lot better than what the published results would suggest. So if you do proper hyperparameter optimization, they're actually they're very cheap and they're surprisingly competitive. So one of the benefits of having a standard library for doing this sort of analysis. So just to summarize before Martin kicks me off the stage, there's been a lot of work done in fairness, but there's been a lot of rolling your own, if you like it, in terms of how people define fairness, how people compare different models, how people do the aggregation and evaluation. Model selection is a surprising bugbear in this space. As I say, NLP traditionally just hasn't really thought about multi-objective optimization problems enough, I would suggest, and it kind of needs to go back to its ML 101 roots and relearn how to do model selection in this sort of a context. And we don't always have to assume access to labelled predicted attributes. Unsupervised methods get us surprisingly far. And I just wanted to call out my amazing collaborators. Some of you will recognise some faces there, many from the University of Melbourne. Thank you.
And as before, we have some time for questions before the lunch, so please raise your hand if you have a question, and you will be given a microphone.
Thank you for your presentation. These days, one hears quite a bit about greenwashing and pinkwashing, and with all the talk about fairness, one might suspect that something might go on like fair washing, if you will. Yeah. Is that something that you're concerned about? And if so, are there any recommendations you have on how to tell the difference between genuine work on fairness and just empty talk, or maybe some watchdog organizations that you would recommend?
Wow, that's a big question. That's a great context to sort of say Fairlib. Use Fairlib and you will hopefully get genuine results. I mean, I would concede that it's very, very rare over anything other than toy data sets where you get truly fair models. There are always disparities. And you see these in the results throughout. If these results are non-zero, it's an unfair model. But compared to a vanilla model, we're doing better. And so for this particular data set, we're not doing that much better. For this other data set, which is a sentiment analysis data set based on standard American English versus African American vernacular English, we get much bigger improvements. But they're still big numbers. They're nowhere near zero. So is that fair washing? Yeah, I would say improvements are good. There's plenty more room for improvement, so I wouldn't claim that we have truly fair models. What I would additionally say is any work that you're doing, if you're not doing some level of audit in terms of fairness and exactly what predicted attributes that would make sense for, it will very much depend on the domain. How you get access to those predicted attributes can be very hard at times. So it can sometimes involve engaging with community groups because maybe for legal reasons in some instances. There's one project we have which is exactly that. We can't ask our users to self-disclose particular predicted attributes. The only way that we could potentially get access to them is by getting synthetic data from community groups representative of some of the particular demographics that we're interested in. So it's hard yakka at times to actually do that sort of audit, but if you're not doing anything, then you should basically assume that your model is bad across one, if not many, different dimensions. But to the essence of your question, through downloading Fairlib and running these different methods, can you kind of wash your hands of the problem and sort of say, you ripper, I've got a fair model? No, it's a better model. And we have to be very realistic about this and very upfront about this, and hence the data audit thing. And if we are deploying models in the real world, it's critical that we're presenting warts and all, those results to the actual users and the host, the organisation who's going to be running this system, so that they know that you have these disparities. And sometimes the answer is going to be, I can't live with that. Scrap AI, that was a silly idea. In terms of watchdogs, it's a harder question. I don't know if there's really sort of watchdogs in any meaningful sense that are sort of looking at this systematically. I mean, you've got lots of whistleblowers, certainly, in the community, but that tends to be sort of individuals rather than organisations. I don't think we're sort of quite there yet. I don't think the importance of fairness has sort of quite reached that level of criticality quite yet. And this is something we need to change.
Hi, thanks for the talk. You mentioned fairness and performance are mutually exclusive.
Not mutually exclusive. There's a trade-off between them.
Yeah, so well, can you elaborate a little bit why that is so? Why ensuring good fairness kind of compromises on your performance?
So possibly the easiest way to see that is if you go back to some of the simpler methods that I mentioned at the start. So the pre-processing method, for example, a simple downsampling method which says, okay, I want to have equal numbers of instances across all of my protected attributes. So if my minority, the smallest demographic group is only 5% of my training data and it's a binary distinction I'm making, I'm throwing out 90% of my training data. My model's not going to be as good. There's no way my model's going to be as good if I've just thrown out 90% of my training data. And okay, that's an extreme example, but and even with the adversarial examples, the job of the adversarial discriminator is to distort the representations that my base model is working. And there's no guarantee that it's distorting them in a bad way, but it's certainly distorting them. So yeah, everything is sort of very complex in terms of decision services, and adversarial methods just make it even worse. If anyone's ever played around with them trying to actually getting them to converge, they'll know what I'm talking about. But yeah, it tends to be that you're taking a hit, and however you structure your model, you're basically, to some degree, undoing the work of the base model, which is doing the optimization for the target variable, in sort of doing this extra whatever it is, whether it's post-processing or pre-processing or in training, to try to achieve a fairer outcome.
Okay, so essentially it's a problem that happens every time you introduce any bias into your system, right? So.
Yes, yeah, to a large degree.
Thanks.
Hi, thank you for a great talk. So maybe directly following up on the previous question, given this fairness versus accuracy trade-off that you mentioned, what incentives can we introduce to encourage companies, encourage researchers to develop fairer models? Do you see any trends, for example, requesting more fairness metrics as a standard evaluation of new models at big conferences, or anything happening in this direction, or should we push for this?
We should certainly push for it, and so I would add to the Morella criterion of if there's no human evaluation, I give it a 1. If there's no mention of fairness, I give it a 1. I mean, that's somewhat tongue-in-cheek. It sort of depends on the task, but I think it's up to us as a community, in research terms at least, to insist on this. And I think if we can make enough noise about the importance and the magnitude and the impacts of unfair models to impress on those who are perhaps more commercially motivated, then I think we can hold the companies more accountable and create more of an expectation that you have these sorts of fairness audits and proper disclosure of the fairness of models. Now, having said all of this, everything I presented here was in a classification setup. Classification is much easier than modern-day generative large language models. How you do, I mean, there are sort of obvious ways to sort of apply some of these similar methods for generative large language models over hidden representations, sure, but does that really stamp out any of these sort of horrible discriminative outputs from the models, or subtler perhaps discriminative outputs from the models? I highly doubt it. But for generative large language models, it's still very much an open research question as to how you do this effectively. And it's much harder to really make any inroads with generative models. But yeah, if we're aware of it and we're banging the drum hard enough, hopefully enough people will pay attention, and we will make progress towards that outcome.
Just for context, 1 is the lowest score you can get for an NLP conference.
Yes, sorry, 1 out of 5.
Thank you. So, very interesting talk. Just to be controversial because
Excellent.
that's where fun lies.
Yeah.
So I guess there is a basic assumption of your talk that fairness necessarily is a good thing and unfairness, biased, is a bad thing. So I come from a medical background, medical AI, and I'll just give you one example that, for example, in a typical situation, if you get a lung nodule, your primary concern is that must be a cancer situation.
Yes.
If you look at people like us from India, tuberculosis means majority of these lung nodules are probably there in the population anyway. So you might say that it's biased to say Indians with a nodule is non-cancerous, because there are also cancerous situations. But that's something of a bias that the healthcare uses because it's resource constrained and it has to reach to a certain level. So when you are really talking about the decision making and the fairness bias situation, how do you deal with this problem?
An excellent question. And taking that to a further extreme, one interpretation of this is personalization is bad. By definition, it's bad because you're trying to change the system output for one user relative to other users. And that's not what I'm saying at all. The premise behind all of this is I don't want systems where I get disparities in terms of the performance based on attributes of the individual that they have no control over. I don't have control over my skin color or my gender identity or anything else. But if I choose to disclose that, or if it makes sense in a particular domain to disclose that and actually use that information, absolutely. And there's also a subtle question of, so for profession classification, say, would I like the world to be a place where there were no correlation between binary gender and certain professions? Surgeons, I would love if that were gender balanced. Nurses, it'd be nice if that were gender balanced. The world isn't that way. So does that mean that my models shouldn't be able to use that sort of information to say that, well, this person seems to be more likely male, so maybe there's a greater chance they're a surgeon? There's a very subtle, very fine line there in terms of, well, this person is female, so there's no way they're a surgeon. Bad. Whereas, I'm nudging the prediction of my models in a certain way based on, much subtler biases. So I'm trying to increase the performance of my model without making it less fair. And for some of these models, that's what you can actually achieve. You can actually achieve higher performance, higher raw accuracy than a vanilla model, say. So there are instances where it isn't, truly speaking, a trade-off. It's more a question of forcing the model to work harder, to sort of not use the artifacts in the data, whether that's based on predicted attributes or other things. So in the sort of context that you're talking about, absolutely, you should make use of that in instances where there's been patient disclosure of that information, say. So with consent, absolutely. But the control needs to be in the hands of the user, I would say.
That's sadly all the time we have for questions. So let's thank the speaker again for the amazing talk.